Here we have an electric field problem involving a line charge and a point charge. So we have a very long charged line with a charge density of 1.7 times 10 to the minus 6 coulombs per meter, and a point charge with a charge 3.7 times 10 to the minus 6 coulombs. Both the point charge and the line are held in place so that they are separated by 0.18 meters. And we want to figure out where the net electric field would be 0. So as always, we'll start with a picture. Here's our positively charged line charge. Here's our point charge Q, separated by 0.18 meters. This is the electric field just from the line charge. So I'm drawing it pointing away from our positively charged line, and I want to make sure I show it in each region: to the left of the line, in between the line and the charge, and to the right of the charge. In a different color now, I'll draw the electric field due to the point charge. So again, it points away from the point charge, and I'm drawing this in each region here. And right away from this figure, we can figure out where the net electric field could possibly be 0. Looking at the direction that each electric field points, we can figure out that it must be somewhere between the point charge and the charge line is where our electric field vectors point in different directions and could possibly be able to cancel each other out. So with that in place, we can start thinking about the math. So I'm going to say there's some point x here where the net electric field I think should be 0. This point x is some distance d that I don't know away from the line charge. That would mean that point x is a distance 0.18 meters minus d away from my point charge. My electric field equations both involve a distance away from an object. So my distance of x away from the line is d. My distance of x away from the point charge is 0.18 minus d. So at point x, if we look at the electric field due to the charged line, that's going to be 2k times lambda over the distance d, pointing in that case to the right. The electric field from the point charge will be kq divided by the distance from the point charge, 0.18 minus d squared, pointing to the left. That's what we figured out when we sketched the electric field. So if the electric field is supposed to cancel out at point x, then E lambda should be equal to EQ in magnitude. So I can set those equal, cancel out the k's, and multiply out the 0.18 minus d squared, and I get the following equation. Let me rearrange this sum so that I get something that looks like a quadratic equation. So 0 equals 2 lambda d squared minus this whole thing is our b term in front of d. If we think of the quadratic equation as a times d squared plus b times d plus c, we have this in that right. We have our equation in that form now, so we can use the quadratic formula. When I do that, put it in my calculator, plug in the values for lambda and q, which we know, and solve for d. It's a quadratic equation, so I get two values. I get that d could either be 0.0227 meters or it could be 1.4226 meters. Well, going back to our original sketch, we figured out that that this point where the electric field is 0, this point x, has to be somewhere in between the line charge and the point charge, and so the value for d must be smaller than 0.18 meters. So based on that, we know that it's the small value is what we were looking for, d equals 0.227 meters. And this was a little bit hairier math than we have sometimes, so it's always a good idea to go back and check now that we're at the end. So if I go back to the electric field equations, use this value of d as the distance from the charged line, I get 1.35 times 10 to the 6 newtons per coulomb as the magnitude of electric field from the charged line. The distance of point X from the point charge is 0.18 minus d, and when I do that math, I again get 1.35 times 10 to the 6 newtons per coulomb. So it checks out, we did everything correct, and we have figured out where the net electric field would be 0, at precisely this point X in between the point charge and the charged line.